In the early 1990s, a powerful new tool emerged in the world of machine learning: support vector machines, or SVMs. These became a popular choice for tasks like classification, especially because they worked so well in complex, high-dimensional spaces. In other words, they could handle datasets that contain a large number of features or characteristics. Let's imagine you're in a classroom populated by two types of students, some who prefer science and some who prefer art. You want to separate these two groups so you can customize a fitting curriculum for them. Let's say you have some information about these students, like their test scores in science and art. You can plot each student on a graph where the x-axis represents their score in science and the y-axis represents their score in art. Now you'll have some dots representing students scattered on this graph. Some dots are science lovers and others are art lovers. Your goal is to draw a straight line on this graph that separates the science lovers from the art lovers. Ideally, you want this line to be as clear and as far away from both groups as possible, so there's no confusion about which side a student belongs to. Here's where a support vector machine steps in. The SVM is like a smart tool that helps you find the best possible line that separates the two groups. It doesn't just draw any line, it finds the line that maximizes the margin. The margin is the distance between the line and the closest points, or students on either side. The SVM finds the line that leaves the largest possible margin on both sides, meaning it's as far away as possible from both groups. This helps reduce the chance of making mistakes when classifying new students. The points, in our case, the students that are closest to the line, are called support vectors. These points are critical because if you move them slightly, the position of the line might change. In other words, these support vectors support the line and help define its position. Now imagine a new student joins the class and you want to know if they prefer science or art. You just check which side of the line they fall on. If they fall on the science side, you classify them as a science lover. If they fall on the art side, you classify them as an art lover. Sometimes the two groups cannot be separated by a straight line in the original space. In those cases, an SVM transforms the data into a higher dimensional space where it can draw a straight boundary, called a hyperplane. When we project that back down to the original space, it might look curved like you see here. But don't worry about the math behind this. Just know that an SVM can handle more complex separations too. SVMs help you find the best line or boundary that separates different groups of data, like our science lovers and art lovers. The goal is to make the separation as clear as possible by maximizing the margin between the groups. Support vectors are the key points that help define this boundary. SVMs are widely used in machine learning to classify data. While the math behind it can be complex, the basic idea is to find the best way to separate different types of data with a clear boundary. Support vector machines are still very much in use today, particularly in fields where clear, robust classification is crucial. They excel in tasks like image recognition, where they help differentiate between objects or even identify handwritten digits. SVMs are also widely used in text classification, such as filtering spam emails or categorizing news articles by topic. In healthcare, support vector machines assist in diagnosing diseases by analyzing complex medical data. In finance, they help detect fraud by identifying unusual patterns in transactions. Despite newer algorithms, SVMs remain a go-to choice for many applications due to their accuracy and ability to handle high-dimensional data.